Okay, so in the last video, we got through all your different biases and study errors, and we stopped right before starting actual biostatistics, right? So now we're going to be looking at topics related to standard deviation, measures of dispersion, stuff like that. Let me see. So with biostatistics, just like everything else we've done so far in epidemiology, you want to make sure that you're not just memorizing it, right? Because it's really like not a memorization game. You're learning math for one thing, right? You're basically learning math here, but you never learn math by just memorizing things. You really have to understand what's happening. So a lot of the things are things you've probably already learned at some point, and some of these things might be things you never really had to learn, like in college or anything. You know, a lot of people basically got into medical school never having worked with standard deviation. It was just not a thing. You know, there was no need for standard deviation in any of the courses you took. A lot of people have never seen anything related to statistics. They have no idea how the null and alternative hypothesis works, right? And then what type 1 and type 2 error are. So it's a lot of new data. It's a lot of new information for you to learn, but it's learnable. It's not ridiculously difficult. You can definitely do it. So the first two things here, they're pretty much stuff you might have a pretty decent idea of. Everyone, generally speaking, does know about the measures of central tendency, your mean, median, and mode. The mean is basically you add up all the numbers and you divide by the number of numbers. So if you have 50 different numbers that you collected, you add them all up and then you divide by 50, and that's going to give you your average. It is the most affected by outliers, right? So a good example to talk about mean, median, and mode is going to be like a class of 50 students that took a test, right? If everyone scored around a 90, the average is going to be a 90. Now, if about one or two students got like a 10 on the test, right, that average of 90 is going to go down a lot. Similarly, if everyone on the test scored like a 70, then the average is going to be about a 70. But if there were like 5 people that got 100, right, that's going to bring the average up a lot, and so on. So outliers, and you can get questions like that. You can get questions where they'll be like, you know, what would affect the mean the most? And then the answer will be whoever is one of the outliers, one of the two extreme ends of a normal distribution, right? Normal distribution is your Gaussian bell-shaped curve, where this end would be someone that got the lowest grade, and this end will be someone that got the highest grade. You have your y-axis right here, like this, right? You have your y-axis and your x-axis, and you have your curve. And this over here are all the people that failed the test with like 0%, whereas these are all the people that passed the test with 100%. This is where most people will fall, right? Getting around half average, about like a 50 to 60% on the test. A lot of people will have about a 70 to 90 on the test, and then above 90. So something like that. Right? So the mean is mostly affected by outliers, people on the far ends. If there's a lot of people that got a really, really low grade, then your average is going to be really low. The median is the middle value of a list of data sorted from least to greatest. So if I take all their test grades, right, so 3 people got a 10, so it's 10, 10, 10. Then I put all the other numbers in order, increasing order, all the test grades, with the last test grade being the highest score, like a 97 or something. That's what you have to do first. You put all the numbers in order of increasing, and then you look at the middle number. Now, if you have an even number of values, like we have 50 tests, then you're going to look at test number 25 and 26 and add them and divide by 2, and that's going to be your median. Right? So the median will be the average of the two middle values. Right? If you have an odd number of tests, like 51 people that took a test, then test number 26, that grade in increasing value, that would be your median all by itself. The median isn't really affected by outliers at all, right? The outliers are still going to be on the outlying aspect of your increasing order, but the middle number will still be the middle number, and it's not going to be affected that heavily by outliers. The mode is the most common value, right? The most common value, and this is not affected by outliers at all, right? The mode is the most common value. So in this example of 50 people that took a test, maybe 7 people all got a 62 exactly. So then your mode is going to be 62. That's the number that was scored the most. And if 3 people got a 0, 4 people got a 0, you know, it's not going to have any effect. You know, of course, now if 7 people got a 0, that just means you have a brand new mode. So that didn't necessarily affect your mode, it changed. You have a whole different mode in general, because mode isn't really calculated, right? Just it's a number that you just have the most repetitions of. You don't calculate mode. You might need to calculate median if you have an even number of values, but even median for the most part isn't really calculated. Then you have your measures of dispersion. This is the stuff that people don't really know. A majority of medical students have never worked with standard deviation and have no idea of how to work with it. Like, they're coming at standard deviation with a blank slate, and that's okay. It's alright. You came into medical school with quite a blank slate too. There were so many things you never knew, right? So many physiology and pathology that you never had any idea of, and of course a lot of pharmacology you had never idea of. So now here's a little bit of math that you never had any idea of. No big deal. Right? Measures of dispersion. So standard deviation is how much variability exists in a set of values around the mean of those values. Right? So like we said, the mean is the average, right? The average is also going to be sort of related to your mode, the most common value, because the most common value will determine your average. If there were a lot of people that got 70s, then your average is going to be pretty close to 70, right? So something like that. So now, standard deviation is centered around a mean. So you look at the average, then you look at how far people are from the average, right? How badly are you far away from the average, or how close are you to the average? And that's kind of what standard deviation is really measuring. Standard error is an estimate of how much variability exists in a theoretical set of sample means around the true population. Right? And standard error is calculated by taking standard deviation and dividing it by the square root of the number of people, your sample size. Right? So this is the equation for standard error. And you can put this on the same cheat sheet we were putting together yesterday too. So I showed in yesterday's video the cheat sheet that you're going to have before your test, and you're going to make muscle memory of it. Right? So where did I put my pen? And you're going to make muscle memory of rewriting this entire cheat sheet before your test, so that you can actually have it there and not need to remember equations. So another thing that you can add in there is your standard error. Standard error is equal to standard deviation divided by your square root of n. So what I did yesterday, when we were doing this yesterday, I showed you guys, let me see, okay, so I showed you guys the bottom half also. Right, the bottom half is where we had all our biostatistics stuff. So you see this equation for the confidence interval, right? The confidence interval has this little portion right here, which is your standard error. Confidence interval is actually calculated using standard error, right? So that stuff in here is exactly what standard error is. So you can rewrite it twice if you want to for now. One thing you'll notice is when you're actually trying to memorize your cheat sheet the week before the test, you'll start memorizing a lot of those equations. You won't even need it on your cheat sheet, and you'll actually be able to take things off of your cheat sheet and maybe replace it with something else the week before your test. So that's something you want to work on for sure. And as we're developing these cheat sheets, when I finish this first part after Biostatistics today, I'm going to take a picture of this. I'm going to rewrite it much more neatly and cleanly, and take a picture of this and post this on the YouTube channel right now, so that you have your cheat sheet for biostatistics and epidemiology, because this is all you need to know in terms of equations for all the math. Now, standard error being something that you can calculate is often asked, right? People will ask you in a question like, what is the standard error in this sample? So you have to be able to calculate it. It's actually calculated by standard deviation, which is usually something that's given, and divided by the square root of the number of people that are in the sample, how many people you have on the test. Right, so now if the 50 people taking the test I made up, your standard deviation, they might tell you like standard deviation might be 10, right? So then your standard deviation, so the numerator would be 10 and the denominator would be the square root of 50, because 50 people took the test, right? Something like that. So the other thing is variance, and variance is your standard deviation squared, right? Standard deviation squared. And again, you will not know, you're not going to learn why these equations are the way they are, right? That's what you missed out on because you didn't really take biostatistics as a course. And you don't need to take biostatistics as a course though. You just need to remember these specific equations, right? If the question is asking you about variance, you take your standard deviation and you just square it. When you square your standard deviation, you find the variance that a certain set of statistical data has. Variance is the calculation of how varied, how far apart, how different is the data you collected, right? Variance will be very, very low if your standard deviation is like 1, right? Because 1 squared is 1. If your standard deviation is 2, 2 squared is 4. So the variance won't be that big. But if your standard deviation is like 50, well, 50 squared is a huge number. So that's going to be a very big variance, and it's going to happen because your data is very far apart from each other. So that's a sign of variance. Standard error shouldn't be that big either. Standard error should be small. Standard error decreases as you increase n, as you increase your sample size. Right? We're going to see as we go on, increasing sample size is known as increasing power. The more power you have, the more people you have in your data, the more I don't want to use the wrong, I was going to say accurate, but the more I guess the smaller your standard error will be is the best way to say it, because it's not an accuracy thing. We discussed accuracy and precision yesterday very well, right? Where accuracy was the trueness, the correctness of the value, whereas precision is how well you can repeat and keep getting the same answer, even if the answer is wrong. Alright, so anyway, that's standard deviation, and we're going to see how it's calculated and how you use it in questions. I have some practice questions too. So the next thing they show you is your bell-shaped curve. You have your normal distribution where you're supposed to assume for this stuff, for a normal distribution thing, your mean is equal to the median and is equal to the mode. Basically, your mean is this big number, this most popular part right in the middle. Right, that is your mean, and that's also your median, because in increasing order from left to right, this is going to be right dead smack in the middle, and it's also your mode. It'll be the number that's repeated the most number of times. So this right here in the middle would be a 50 maybe, right? So out of my 50 people that took the test, maybe 40 of them actually got a 50, so that is going to be your average. That's also going to be your median, and it's going to be your mode, right? So that's kind of what happens in a normal distribution. And if that changes, if you don't have your mean is equal to median is equal to mode, then you're going to get non-normal distributions, and we'll look at that next. So now when you're given something like this, when you're given a standard deviation bell shape, and this is usually what you'll get on your test, you're not going to get questions on any of these guys. If they give you an image like this, they probably want you to be able to identify how the mean, median, and mode are going to be related, and we'll get there. But for the most part, most numerical calculation questions you're going to get are going to be based off of a graph like this. So you see how here they tell you, right, the middle line, the highest point, the dead smack in the middle, that is your mean, median, and mode. So let me zoom in for a little bit. Where'd it go? Okay, right here. Alright, so this middle portion here is your mean, median, and mode. If you go -1 standard deviation, right, or +1 standard deviation, 1 standard deviation covers 68% of all test grades, right? If you go 2 standard deviations, that covers 95% of all different test grades, and the 3 standard deviations is almost 100%, right? 99.7. These percentages are great to memorize, that's fine, but the more important thing to realize is that this covers 2, not just 1. So +1 standard deviation is actually just 34%, right? Because 34 plus 34 would give you 68. So +1 standard deviation is only 34%. This area over here in the white, the +2 standard deviation, this is 13%. 13%, right? Because 95 minus 68 would give you a number. You divide that by 2, you get your 13% right there, right? And then this last percent here, the third standard deviation, this is about 2.5%, but you can just leave it at 2% for easier math, and then find the answer that's closest to 2 or 2.5%. Not many answer choices are going to be very similar to each other. And why is that significant? So basically, this same kind of graph can be given to you, and they'll tell you that this is the Gaussian curve for a population of maybe 100 people whose blood pressures were taken, right? So then most people would have normal blood pressure, and that would be right here, 120/80, right? And then they'll tell you that the standard deviation of blood pressures was maybe 10, right? So in the middle you have 120/80 plus 1 standard deviation would be 130/80, right? We're gonna say that we only calculated systolic, so let's just look at systolic. So here it's 120, right? Plus or minus 1 standard deviation would be 110 or 130, right? So you could calculate how many of the people must have gotten a blood pressure within one standard deviation. If you're looking at within one standard deviation, you go both ways, -1, +1. So you're going to look at all the people that got something between 110 to 130. And that's going to cover 68%. So since I just said we took blood pressure of 100 people, 68 people would have a blood pressure of 110 to 130, anything in between that. If the question asks you how many people probably got a blood pressure of more than 130, more than 130, well, more than 130 means that you're not going to be looking right here, because this is everyone that has 130. So more than 130 would be in here and everything else, right? All of this stuff, more than 130. So this area here is 140, this area is 150. Everything after that is all the people with 160, 170, 180. So what is this much percentage? Well, if right here is 34, the rest of that is 100 minus 34. So 66, right? So 66 people would have a blood pressure of more than 130. You have to be able to understand that these percentages are only telling you some information. There's a bunch of other information, right? There's a lot more happening. For the graph from just let me see, how do I comment? Okay, from right here to here, this is also 100%. Right? This is also 100%. This portion right here. So I just told you this portion right here is 34%. Right? This one here is 34 plus 13 if you add both of them. But this alone is just 13. Right? And then this one here, this tiny portion here is also just 2%. Right? 2 or 2.5%. That's about it. Nothing much in here. You keep going, you get like 0.5% for this area. Everything is supposed to add up to 100%. Right? Whereas what they're doing here with this big one, they're saying that if you look at plus or minus 1 standard deviation, that's a whole different way of looking at it. Okay? So two different ways to look at the same graph. It really depends on what's being asked. Okay, you have to look for the question being posed to really be able to understand what's happening. And we're gonna see some practice questions. I think I put it in here already. Otherwise, if I don't have practice questions ready, I'll do a separate video just to do practice questions so we can revise this stuff. But make sure you understand how this graph is provided, right? Because questions are very straightforward. They're not that confusing, and you have to make sure you understand which way you're supposed to go, plus or minus 1 standard deviation, and then how much is within 1 standard deviation, each one of them. And that's what I put over here, right? So 34, 13, and 2, right? And the whole thing itself is also 100%, like they said, right? So basically, this entire thing from end to end is 100% as well, right? Two ways to break it down. If you break it down in this way, then yes, right? Because this is 68, so this is 34% right here. Because 34 plus 34 will give you 68. Then let me see. Let me just make sure that the math is correct here. 95 minus 68 is 27 divided by 2, so 13.5. Right, so this would be 13.5 right here. 13.5. I wish I could write more clearly with the mouse. 13.5. Okay. Right, because 13.5, and then this would also be 13.5 here as well. So these are both 34, 34. Right, this is also 13.5. And then the last thing, you're 99.7, so 99.7 minus 95 is 4.7. Divide that by 2, you get 2.35. So this one here would be 2.35% of your 100%. This is also 2.35. Right, so only 2.35% of people will have a grade really, really low, or a blood pressure really, really low. Go with any example I'm going. So if we keep with the blood pressure example, we said that right here are all the people that got 120 on their blood pressure, systolic, right? And I told you that standard deviation for our little example that I'm doing, standard deviation is a systolic change of 10. So then everyone here, dead smack in the middle, had 120. So plus 1 standard deviation, this is everyone that got something between 120 to 130. Right, that's 1 standard deviation. Here would be all the people that got something from 130 to 140. See? And going the other way would be the other thing. So this would be everyone here in this column of minus 1 standard deviation. This would be all the people that got a blood pressure of 110 to 120. Right? Because I'm going minus standard deviation. So I'm taking 10 away. And this one here would be everyone that got a blood pressure of 100 to 110, right? So now your question can ask you, how many people might have had a blood pressure within 2 standard deviations? So within 2 standard deviation means minus or plus, right? So you have to go both ways. So going both ways, that's 95%. And since I said 100 people were collected, right? The N is 100 people whose blood pressure was collected. You can easily calculate the 95 people must have had a blood pressure between 100 to 140, right? 100 to 140, because that is within 2 standard deviations. And that makes sense, right? If you actually collected blood pressure in a huge community and you actually picked out 100 people and took their blood pressure, and they're all mixed kind of people, right? They're not all elderly, they're not all obese, they're mixed people. Some are healthy, some are not. When you do something like that, yeah, Ladine, I'm gonna all my lectures are uploaded. So if you find the playlist called Full FA 2019, every single lecture I've been doing lately is in there, and you can rewatch anything anytime you want. Let me grab the mouse so I can fit this correctly. There you go. So what we're seeing here now is different ways of asking questions, right? So within 2 standard deviations, we got everyone from 100 to 140, and that makes sense, right? If I took 100 people from a mixed population and took all of their blood pressures, about 95 of them would have a blood pressure that fell between 100 to 140, right? How many people are really going to have a blood pressure below 100, and how many people are going to have a blood pressure above 140? Not that many, right? There will be a few. That's going to be your 2.35% of people who are going to have a blood pressure of more than 140, and 2.35% of people who will have a blood pressure of less than 100. And since for ease I chose 100 people, so about 2 people would have a blood pressure of less than 100, about 2 people or 3 people would have a blood pressure of more than 140, and that's it. Right? These are all the different ways you calculate statistical data based off of the knowledge being presented in a Gaussian curve. Alright, so the other thing this Gaussian curve tells me is that 120 is my M3. Right? M3 being your mean, median, and mode. 120 is your mean. That's your average blood pressure in this population. It's also your median. It's the middle number of all the different blood pressures that are collected here. And it's also the mode. It's the most common blood pressure being collected, right, in this example that I'm showing you guys. So a lot of data is given when a Gaussian curve is provided to you. Remember, a graph looks like no information to you if you have no idea how the graph works. Right? If you don't know how to read the graph, then it's basically like being presented some kind of Arabic literature and you don't know how to read Arabic, you have no idea what you see. So you have to learn the language, right? Math is a language. You have to learn the language, you have to learn how to read the curve, and that's what I'm hoping that this is making a little more clear for you guys. Alright, now let's undo all of that. I wish there was a quicker, clear button or something. I love this PDF reader though. It's so nice to be able to like write on the PDF directly like this, just for teaching purposes, and then easily undo it. Go back to full page. Alright, so that was our Gaussian curve, right? The normal Gaussian curve. This little note about this picture. So the red line on the left image depicts increased precision, right? There is a way to see accuracy and precision on a Gaussian curve. This is something that the book doesn't talk about at all, so I want to make sure we don't miss that. Right? There is a way to look at, let's see, maybe 200. Look at precision and all of that on a Gaussian curve too. So I just want to zoom in a little bit, really. Okay. So if you look at, no, don't move. Okay, if you look at this curve, right? The normal Gaussian curve was the blue one, right? And our standard deviation was given like this. Now, if you look at the red curve, it became slimmer. Right, it became slimmer. That is a more precise curve than the other. There is no accuracy in biostatistical Gaussian curves, right? Because accuracy is validity. It is the correctness of any data being collected. But there isn't always correctness to data being collected, right? So here we're looking at precision. Data being collected can be precise or not be precise, right? Because it depends on what the data you collected. Did you use the right equipment? Did a lot of the people give you the same responses? And And you can see that this is more precise because it looks like majority of your numbers are going to be the same, right? Whereas here we had a bigger standard deviation. We ranged all the way from maybe 0 to 100, whereas now it looks like everyone scored between 30 to 80, right? Something like that. So if you're ever given multiple Gaussian curves and they're asking you to compare them, the slimmest curve, the slimmest and tallest curve, of course if it gets slimmer it will get taller because the number of people isn't changing, right? This axis here is your number of people, whereas here is your score. The x-axis is the score. So the number of people isn't changing, so if you make the curve skinnier, it's going to get taller. The skinniest and tallest curve, is the most precise one. And then the accuracy part. If that graph is shifted left or right, then the accuracy would also be decreased. That really depends on, there is no solid way to talk about accuracy when it comes to biostatistics. That really depends on the question being presented. Depends on what the data being collected was, right? Because, for example, if the question told you that the correct value should be 120, right? Because there's no correct value for blood pressure. Blood pressure can be physiologically normal or pathologically high, but you don't call a higher blood pressure incorrect, right? It is their correct blood pressure, it's just the pathological number. So if in the question they tell you that the correct number we're looking for is maybe 120, then you want to make sure that the curve is right in the middle because you want that 120, right? If it's shifting to the left and the curve is more towards all 100s or 90s blood pressures, that has lesser accuracy, right? But if it's really high, if the curve is still really high and skinny but it just shifted to the left, this curve is, the height and skinniness of the curve determines how precise it is. The curve being dead smack in the center like that determines how accurate it is, right? So let me write that out right here. Okay, so precision on a Gaussian curve is determined by the curve that is skinniest and tallest. Accuracy on a Gaussian curve is determined by whether or not the curve is in the center, where mean is equal to median is equal to mode, right? If your curve is not centered, and that's what we're going to see next, this is where we're going to. So if your curve is not centered like this, all beautiful and symmetrical like that, if it's not symmetrical, accuracy has gone down. Accuracy doesn't increase. You have 100% accuracy if the curve looks like this. Accuracy is going to go down if the curve is shifting to the left or the right. And that's what we're seeing over here somewhere, right? You can see how majority of it has started shifting to the right over here. A lot of it has started shifting to the left over here. So that's what it means to decrease accuracy. These two graphs down here, positive skew and negative skew, these two graphs over here have lesser accuracy than normal distribution, right? And the highest precision is when the curve is really, really skinny and tall, right? So those are two comparisons that the book does not make, but you can definitely get tested on it because they talk to you about what is precision, what is accuracy. They just didn't connect it to a Gaussian curve, right? So now we learned something that wasn't in first aid, but you can get an easy question on. Now we look at non-normal distribution. What are non-normal distributions? So these are all distributions that are not normal simply because your mean does not equal your median and that does not equal your mode. So let's look at how these non-normal distributions look. First thing we have are bimodal. And this almost always is going to be about a Hodgkin lymphoma thing, right? Because Hodgkin lymphoma can affect people that are really, really young. It can affect people that are really, really old. And in the middle, it doesn't really affect middle-aged people that much. So this would be an x-axis with age. The y-axis is always the number of people being affected. Right, so this would be all ages. So you could see like people around age 20 would be affected, and around age 60 would be affected. But people between 30 to 40 are not really being affected that much. So that's what a bimodal graph looks like, right? Instead of everyone having a single thing where it's the highest, there's two places where it's the highest. Right? So this is why it's bimodal. Bimodal, see, two modes. Two modes is what bimodal means. There are two numbers that are repeated the most number of times. Right? So there's maybe, if this is a population of 100 people again, there might have been 30 people that got 20 years old and 30 people that got it at 60 years old. So you have two modes, 30 and 60, which is why it's bimodal. Right? Super easy to understand. If you're given a curve like this, it just means that you have to first understand it's not normal. Right? So the distribution is not like a Gaussian curve. Second, you have to understand that the median and mean are going to be altered heavily. And third thing you have to understand is there's two modes. There's two modes, so you can't really pick one. Then you have your positive and negative skew. Now what people forget or don't tend to know how to memorize is, how do you understand this one is a positive skew and not this one? Right? Because you have to memorize by looking at the graph, you have to be able to memorize what it's called. So the reason this is a positive skew is because remember your y-axis is over here, right? So this is 0 and this goes to 100 or whatever, depending on whatever you're calculating on the x-axis. Let's say for our example we're doing still age, right? So your x-axis is still age. So this is maybe 100 years old, 0 years old. You see how most of the numbers have gone towards 100 years old? So that's a positive skew. Positive skew meaning that you went further away from 0. Whereas if you came closer to 0, a lot of the numbers are moving towards 0, right? You see how all of this, the tail came all the way over here, now it's towards the 0 people. A lot of the outliers are closer to 0. That's a negative skew. More people are coming towards 0, more people are getting this disease, whatever this disease might be, is more common now during the younger ages, and it doesn't occur at old ages at all. Whereas over here, this disease doesn't occur at young ages at all, but it does occur in older ages. However, both diseases are most common during the middle-aged years, but you can see that their modes are different too now, right? In your positive skew, your mode is actually very, very much closer to 0. Whereas in a negative skew, your mode is much further away from 0. So things are different. They are different. So positive skew, you use the more than sign. More than, right? Remember in math, this sign, when it's facing like that, that's called more than. Whereas when it's like this is called less than. So it just perfectly fits in. Positive is more than. So you still write mean, median, mode in that same order. The same order that we've always been writing it. You still write mean, median, mode in the same order, but positive skew. So mean is higher than median, and median is higher than mode. So if you're given a bunch of numbers, the mode should be the smallest number, the median is higher, and your average is really, really high. Remember, average is affected by outliers the most, and you can see how all your outliers are closer to 100 years age. So your mean is also going to be closer to 100 years age. Mode is not really affected by outliers that much, so it doesn't really shift that much, right? It's just going to stay somewhere in the middle. So mode is simply the number that's been repeated the most number of times. It's not something you calculate, so it doesn't get affected by outliers that much. In a negative skew, right, you can see it's the other way around. Less than. Use the less than sign for negative. Right, so mean is less than median, and the median is less than the mode. Your mean is again the smallest number now because all your numbers are closer to 0. So that, remember, outliers affect your mean the most. So since you have a lot of numbers that are less than 40, your mean is also going to be less than 40. And this is how you have to be able to catch questions, because they're going to give you a bunch of numbers and they're going to be expecting you to be able to figure out which one is the mean, what's the median, what's the mode, or if it's a positive or negative skew, etc. Right, so here I have some kind of example. It says positive skew, so the mean equals 20, median is 15, mode is 10. There must be many numbers greater than 20, so the mean is high, right? Whereas in a negative skew, your mean could again be 20, median 25, mode 30. So you can see how the mode is the biggest number now. There must be many numbers less than 20, so the mean is low. But in both of my examples, the mean is 20, right? Because they're completely different sets of data, so it doesn't matter that the numbers are 20 still. You look at each set of numbers as a different set of data. For skewed distributions, the median is a better representation of central tendency than the mean. Remember, these are all things called measures of central tendency, right? And in a normal distribution, the center was your mean. But in a non-normal distribution, the median is in the middle, appropriately, right? So the median tends to be a better representation of central tendency than the mean. So if you get a question where they give you a non-normal distribution and they tell you majority of people were on this side, so it's a negative skew, or a majority of people were on the upper side, so that's a positive skew. If they give you something like that and you can tell that this is not a Gaussian curve, right, because they might not necessarily give you the curve, they might describe it verbally. They might describe the data to you verbally. Or they might just give you the data where you're looking at 100 different people's blood pressures and all the blood pressures seem to be near 90. That's a negative skew, right? If that stuff is happening and then they ask you which number would be the best representative of central tendency, do not just pick mean as your answer. This is a non-normal distribution. If mean was the best measure of central tendency, this would be a normal distribution in that case. In a non-normal distribution, the median is the best representative of central tendency. Right, so make sure you pick that as the correct answer as well. It's another topic that the book doesn't talk about, but you can easily get a question on because it is a very realistic biostatistical thing, and the book did teach you what a median is. In fact, they even give you visual lessons of telling you that the median is your central representative, right? Central tendency is going to be determined by the median because it's actually in the middle. Right, it's the bar in the middle now. So although they didn't verbally tell it to you like I did, they did show it to you. The mean is at the tail end, which is described by the word positive or negative. Right, positive skew, mean is large. Negative skew, your mean is closer to 0. Alright, so that's it. This is very important information, very straightforward information. Again, like I said before, throughout biostatistics and epidemiology, none of this is as hard as cardiovascular physiology and respiratory physiology. It's just slightly annoying because, a lot of us tend to make things worse for ourselves by telling ourselves, why do we need to know this? Never going to use this again. Sure, you might never use it again, but it's okay. It doesn't matter. You need to know it, and you can know it really easily, and you can definitely get it correct. You can get it correct. There's a higher chance of you getting this correct than getting some kind of intense cardiovascular physiology question correct. Because those answer choices look really fucked up, and a lot of them seem to sound the same. Whereas here, you just got to pick a number, and you know the number you're looking for. Right? I've always loved math because there was no guesswork. It was literally just calculating and knowing what's correct. Now, that was the mathematical stuff. Now we go into more hardcore actual statistics. So statistical hypotheses, right? Anytime you do any kind of experiment, there's a reason you're doing it. You're trying to measure something, and you're trying to figure something out. So let's look at how do you start a statistical data collection. First thing first, you have to figure out whatever you're calculating, why are you doing it. So there's a null hypothesis and an alternative hypothesis. The null hypothesis, H0, is the hypothesis of zero difference, no difference or relationship. So there is no association between the disease and the risk factor. For example, we might be doing some kind of statistical experiment or something, data collection, where we're trying to see the relation between smoking and lung cancer, right? The most classic example. So the null hypothesis would be there is no relationship between smoking and lung cancer. Your alternative hypothesis is the hypothesis of some difference or relationship. So that would be that there's definitely some relation between smoking and lung cancer. That's it. It's just a hypothesis. Now, right here, this is how we're doing research, right? So first, define the research question. What is it that you are trying to show? Then define the null hypothesis, which is generally the opposite of what you hope to show. The null hypothesis says that the findings are the result of chance or random factors. Right? So there's no relationship. If you want to show that a drug works, the null hypothesis will be that the drug does not work. We never accept the null hypothesis. We either reject it or fail to reject it. Saying we have sufficient evidence to reject it is not the same as being able to affirm that it is true. The alternative hypothesis says what is left after defining the null hypothesis, so the drug does actually work. And this is a very important thing, right? Just because you couldn't prove something is, let me rephrase that. Just because you couldn't prove that something has no relationship. Now I don't know how to explain this without making it more confusing. Because the null hypothesis, we never accept the null hypothesis. We either reject it or fail to reject it. Right, so something has no relationship. Okay, if you prove that two things, smoking and lung cancer, has no relationship, you're going to go ahead and basically fail to reject, right? You're going to fail to reject your null hypothesis. Your null hypothesis says there's no relationship. You don't accept the null hypothesis, though, because although I couldn't show there's a relationship, there might be something there, right? So you never pick the answer choice that says accept the null hypothesis. That's a trick answer choice. You do not pick it. You either reject the null hypothesis or you don't reject the null hypothesis because you were unable to show a relationship. If you showed a relationship, right, if you do show a relationship, then your alternative hypothesis becomes true. Hypothesis of some difference relationship. There is some kind of relationship, right? So saying we have sufficient evidence to reject it is not the same as being able to accept it, right? Just because I prove something false doesn't mean that the opposite is definitely true, right? You still have to prove the opposite is true also. It's two different kind of things that happens in statistics, and it's a very common thing in research. A lot of people, what they'll do is once they fail to show some kind of relationship, they'll try to trick you into believing, oh look, see, they're not related, so we can accept the opposite, which is they're not related, so it's okay, it's safe, and it's not, right? There is no accepting the opposite. You simply rejected what you were trying to prove. You were unable to prove what you were trying to prove. It doesn't mean that you proved anything else, right? Every single thing has to be proven in a whole different way. So that's your null hypothesis, that's your alternative hypothesis, and those guys go on a table like this, which, again, from yesterday's stuff, right, when we made our cheat sheet, we put it all onto the same table, right? So we have our big table right here with our A, B, C, and D in the middle, right? We have, on the edges, we have our true positive, false positive, all that stuff, and then in the center of each box, we have the alpha, beta, and all of that. Right, alpha, beta, everything is in the center. That's basically me reiterating this reality versus what's actually happening in the study onto the same table. You want to be able to redraw all of that every single time because you're going to be able to solve questions more easily. So reality versus study is pretty much still the same as disease versus exposure and all of that. That didn't change. So that's why we were able to use the same table for all the same information. Now what's happening here? So you see H1 and H0, right? H0 is that there's no relationship. So that's why this goes under not having disease. Whereas H1, there is a relationship, so that's like having disease. This is like smoking, right? So if smoking has a relationship, right, then that's power, right? Power, 1 minus beta. Whatever the study was, the study rejected the fact that there is no relationship. You reject your H0. Right? You never accept it, but you rejected it. So you rejected the fact that there's no relationship, which means there might be some relationship, but you don't know that yet, and you're going to have to do another research to find the relationship. Right here, beta is a type 2 error. What is a type 2 error? Remember type 2 error? What goes over here? It really helps to have this table, because on that table, what else goes over here in a similar spot? Your false negative. Right? Under beta, false negative. False negative means that you had the disease, but you got a negative test result. Had the disease, but you got a negative test result. That's a type 2 error, right? So basically, H1. So there is a relationship. Your alternative hypothesis seems to be correct. There is a relationship, but you did not reject your null hypothesis. So if you didn't reject your null hypothesis, that means you pretty much, accepted it in a sense. If you did not reject your null hypothesis, but there was a relationship, then you fucked up. There's something wrong in the experiment, and you have to redo it, or somewhere along the road you made a mistake in collecting data. Whereas over here, what was over here? That was your false positives, right? This part was false positive. False positive meant that there is no relationship, there is no disease, yet you said there is disease. A false positive, right? So again, H0 means there's no relationship, yet you're rejecting the fact that there's no relationship. The truth of the matter is there is no relationship, but you're rejecting the fact that there's no relationship. That's an alpha type error. And you have to be able to understand what alpha and beta mean in terms of type 1 and type 2 error. Thankfully, they're numerically and alphabetically the same. So alpha is type 1, beta is type 2. how do they work out? So how do you memorize what type 1 and type 2 are? So type 1 error alpha, stating that there is an effect or difference when none exists. Right? Stating that there is disease when none exists. You could see the synonymous activity that's happening here, right? How similar everything looks according to the 2x2 square that we have. So alpha is like false positive, whereas beta is like a false negative, and that's what your two different errors are all about. So stating that there is an effect or difference when none exists. So the null hypothesis is incorrectly rejected in favor of the alternative hypothesis. Alpha is the probability of making a type 1 error. P is judged against a preset alpha level of significance, usually 0.05. If P is less than 0.05 for a study outcome, the probability of obtaining that result purely by chance is less than 5%, which means that this is a good thing, right? This is also known as false positive error, right? Which makes sense, right? That's why it's great that we put it all, this one right here, false positive error. So it's great that we put it all in the same 2x2 square. So basically, alpha means you accused an innocent man. You can never prove the alternative hypothesis. You have to do a different research for that. But you can reject the null hypothesis as being very unlikely, right? And here, this was someone that got a false positive, right? H0, there is no relationship, yet you did not reject it, right? Study rejects it. Okay, so you were supposed to not reject it, but you did, right? Even though there is a relationship, and that's what type A is, right? So just remember that as a false positive, because we're putting it on the same 2x2 table. A false positive, there is disease, yet, there is no disease, there's no effect, there's no difference, right? None exists, false positive, there is no disease, yet you said there is. That's your false positive type 1 error. Type 2, also known as a beta, and the reason all this wording is different now is because we're not talking about blood tests and results and stuff like that. Now we're talking about statistical data and biostatistics, right? So there's of course overlap and everything looks different in different fields of work, but it's still pretty much the same concept. So type 2 error, we said, is very much like your false negative, which goes right here, right? Stating that there is not an effect or difference when one actually does exist. Or, in other words, stating that there is no disease when you actually have disease, right? Null hypothesis is not rejected when it is in fact false, and you should have rejected the null hypothesis. Beta is the probability of making a type 2 error. Beta is related to statistical power, which is 1 minus beta, right? Power, 1 minus beta, which is the probability of rejecting the null hypothesis when it is actually false, right? What is the probability of rejecting null hypothesis is actually false? 1 minus beta. You just calculate that in. They'll probably give you what beta is on a table like this. So beta, you blindly let the guilty man go free. I mean, these are all ways to memorize things. If you want to use that, you can go ahead and use it. For me, putting it all into the same 2x2 table made it very evident what we're looking at. So false negative error, false positive error, right? Alpha and beta. Very straightforward now to really understand biostatistically as well as medically what these errors are doing, right? So here, this was your false positive. You gave it a positive test result even though it wasn't supposed to be, and that's bad, right? And this is your false negative. You said that there is no relationship even though there actually is, all right? So that's your two different errors. They tell you now power is increased by decreasing beta, right? Decreasing your type 2 error increases power, which makes sense, right? Because then if type 2 error was 0, then 1 minus 0 would be 1. 100%. And this is done, you can increase your power by increasing your sample size, which everyone always remembers. That's the only one most people tend to remember from students I've worked with. So making n bigger, right? Increasing sample size. For your research, instead of doing it with 10 people, if you do it with 100 people, you'll get more data and it'll be better data, more valuable data. You can also increase expected effect size, right? So for example, if you're testing medication and it's supposed to have the ability to bring down blood pressure, you don't want to check for an effect size of bringing down 180 to 110. Make it a little more reasonable, right? So increasing expected effect size basically means that you made it more reasonable. And then the last thing, increasing the precision of measurement, right? Precision, using better equipment. And remember, increasing precision is not increasing accuracy. Increasing precision basically means that you keep getting the same data And this is done by using newer equipment, making sure that the equipment has been calibrated, has been checked, stuff like that. Alright, power is directly related to type 2 error by the 1 minus beta, and just as increasing the power of a microscope makes it easier to see what is going on a histological slide, increasing statistical power allows us to detect what is happening in the data. Power can be thought of as the probability of not making a type 2 error. Alright, so we just talked about a lot of shit. Just make sure that you can kind of compare it to the false positive and false negative stuff that we've been looking at from the previous 2x2 tables, and really get a better idea of understanding how to talk about it in terms of null hypothesis. Null hypothesis. Null. Null means to void it, right? Null and void. Null hypothesis is basically saying there's no relationship, which is pretty similar to saying there's no disease, right? So here this is a false positive because you said there's no disease, right? But yet you rejected the null hypothesis, and your null hypothesis does say there's no disease. So you're saying two different things at the same time, and that's an alpha error. Whereas over here, H1 is your alternate hypothesis. This one says that there is disease. So if there is disease, you should be rejecting the null hypothesis, but the study does not reject it. So if you did not reject the null hypothesis, which says there's no disease, yet there is disease, that's again saying two different things, right? Those are two counterintuitive things. They should not, you can't have disease and not have disease. You have to pick one, and that's what's happening. So the accurate answer, right, the one that we have not talked about, which is this box right here, the correct answer is null hypothesis not being rejected, right? Your null hypothesis did occur, which means that there is no relationship, so you did not reject your null hypothesis. That's correct. This is power. This is you proving what you were trying to do the research for. Remember when you started the research? You started the research to prove something. Your null hypothesis assumes the opposite. So if I started a research to prove that smoking does lead to lung cancer, my null hypothesis will be that smoking does not lead to lung cancer. If my outcome is basically all this, then that's the correct outcome because it went with my hypothesis, the null hypothesis. Remember in science, hypothesis was your theory. It's what you think is going to be the outcome of the test. For some reason in statistics, the way they do this thing is they have a null hypothesis which goes opposite to what you wanted to prove, and then you try to see if you reject the null hypothesis or not. You never accept your null hypothesis. You either reject it or you do not. And if you were unable to reject it, study does not reject the null hypothesis, right, then that's the correct thing. That means that your null hypothesis ended up just validating itself, right? Whereas here, this is power. This means that your sample size was so big that you were able to actually see some correlation between smoking and lung cancer. Maybe you did 1,000 people in this statistical data that you were collecting. You used 1,000 people, and you were able to see, because of this bigger sample size, you were able to see that there is an association between smoking and lung cancer. So you rejected the null hypothesis, which says there's no relationship, and H1 occurred. H1 is your alternate hypothesis, which says there is some relationship. You just don't know what yet. The last thing on this stuff is your confidence interval, which you get questions on as well. And this isn't that complicated. It's complicated if you try to master it. But all you need to be able to do is answer the question correctly, right? That's all you're really trying to do. You're not trying to become a biostatistics person. You're not trying to become someone who's proficient at working with statistical data. So confidence interval, the range of values within which the true mean of the population is expected to fall with a specified probability. This means that this is the number of people you have to look at to be able to find the correct average, right? The average score of the blood pressures that we looked at, right? The average blood pressure we said in a normal Gaussian curve should be 120. That's going to be in the middle. That's going to be your mean, mode, and median. So within how many standard deviations do you have to look to find that mean? So confidence interval can be calculated. Confidence interval for a sample mean, any mean, whatever the mean might be, the average, right? That confidence interval is equal to the average plus or minus z is a number, z times the standard error. And remember, standard error was calculated with standard deviation divided by the square root of your sample size. So you find standard error first by using standard deviation, divide the standard deviation by the square root of your sample size. So if we did 100 people, the square root of your sample size is 10, square root of 100 is 10, and if our standard deviation is also about 10, like we said for that blood pressure example, then your standard error is just 1, right? And Z really depends on which confidence interval you're looking for. Are you looking for the 95% confidence interval? Are you looking for the 99% confidence interval? Depending on that, you pick your Z, right? And don't use these numbers. Don't use 1.96 and 2.58 because then you're going to really make your math really hard. Just work with 2 and 2.5. You're going to get a number that's close enough to be able to pick the correct answer choice for your multiple choices. So here you have your mean plus or minus your Z times standard error. We said that the mean was supposed to be 120 for our blood pressures. We said Z is going to be 2 if we're trying to do 95%. And standard error was 1. So it's going to be 120 plus or minus 2. Right? So our confidence interval for the sample mean would be 118 to 122. Blood pressures of 118 to 122 will maintain the mean. Right? Population is going to fall in there. And that is true. 95% of people will hopefully in this confidence interval have that mean, if our standard error and standard deviation and all that has been calculated correctly, right? And this is used very often. This confidence interval is exactly what helps you determine whether or not your data was significant, right? There's another thing we saw so far. We saw this. P has to be less than 0.05. For a study outcome, the probability of obtaining that result purely by chance is less than 5%. You need P to be less than 0.05 because if it's more than 0.05, then there's a very high chance the study outcome was just by chance. So it's not that there was a relationship, it was just by chance. It just happened. So you need to decrease that possibility of things happening just by chance by having a bigger sample size. Confidence interval is the other way to figure out if your data is actually significant. So you look at it. If the 95% confidence interval between two variables includes 0, right? So you're doing the 95% confidence interval, you calculated this, you calculated your confidence interval by doing this equation, right? And you did mean plus or minus whatever, and maybe the mean is 1 and plus or minus 2. So 1 plus or minus 2, so that's going to be from -1 to 3, right? -1 to 3. That includes 0, right? -1, 0, 1, 2, 3. Now that includes 0, the 95% confidence interval includes 0, there is no significant difference and your null hypothesis is not rejected. Right? Right? Because that's exactly what your null hypothesis says. Null hypothesis says there's no difference. There's no significant difference. So you end up not rejecting your null hypothesis, which is really funky language because you're so inclined to say you end up accepting your null hypothesis. Don't ever say that. Don't ever pick that answer choice either. You will see it as an answer choice. Don't pick it. Right? It is never statistically correct to say you accept your null hypothesis. You don't. You either reject it or you don't reject it. So here, if 0 is in your 95% confidence interval, then that means that there's no difference. No significant difference. Your null hypothesis is not rejected. If the 95% confidence interval for an odds ratio or relative risk, right? So now we're looking at a whole different thing. The question might tell you what the odds ratio or relative risk for a certain statistical data you collected is, or you might need to calculate it, which is why, again, combining all three of those things into the same table really helps, right? Because when you have all three things in the same table, you could see in the dead smack in the center I have the A, B, C, D stuff, which you would use to calculate your odds ratio and relative risk. So using the same 2x2 table, you'll be able to calculate the odds ratio, calculate the relative risk, etc., etc. If by calculating any of those things, if your odds ratio or relative risk includes 1, then again, there is no significant difference and the null hypothesis is not rejected. Right? And this is a really big deal. If you're unable to reject your null hypothesis, your research pretty much went to waste because you were trying to reject your null hypothesis, right? The main issue was you're proving something, smoking is related to lung cancer. Your null hypothesis is the opposite of that, smoking is not related to lung cancer. You want to reject it. You want to reject your null hypothesis for you to have a successful research. If you got any of these issues where your 95% confidence interval for the mean the average of numbers includes 0, or the 95% confidence interval for the odds ratio or relative risk includes 1, you have a problem there. And then your null hypothesis is not rejected, your research didn't show anything. Last thing, if the confidence interval between two groups do not overlap, then there is statistically significant difference, and that's a good thing. You want the difference to exist because then you go ahead and reject your null hypothesis, right? So confidence interval between two groups do not overlap. Statistically significant difference exists. And that's another thing you might have to calculate. There might be two different experiments that occurred, and you calculate both of their statistical confidence interval, and one might have a confidence interval from 90 to 100, the other might have a confidence interval from like 110 to 120. There's difference, there's no overlap, so you go ahead and reject your null hypothesis. There is statistical difference. If the confidence interval between two groups do overlap, usually no significant difference exists. For example, in the same blood pressure stuff, if one confidence interval calculated from 100 to 110 and the other one calculated from 108 to 118, there's overlap between the 108 and 110 area. So then there's most likely no significant difference. And then you have to check for the p-value. Is it less than 0.05? All of that happens. You do not reject your null hypothesis. You were unable to reject it. Your experiment didn't show anything. Now let's look at some of these questions that we have here. So the first one right here, researchers are designing a study to test hypothesis that a new beta blocker with fewer side effects will decrease the mortality associated with MI compared to the standard of care. They want to make sure that they don't incorrectly ascribe a difference between the new beta blocker and the standard of care if there isn't one. Which parameter do they want to maximize? And this one was such an interesting answer choice because you see 1 minus alpha is not a thing here. Right? 1 minus alpha is not a thing here. But what is it that they're trying to maximize is what the question is asking. So they describe something. They want to make sure they don't incorrectly ascribe a difference between the new beta blocker and the standard of care if there is not one. Is that a false positive or a false negative? Alright, that's the first thing you want to figure out. Is that a false positive or a false negative? They want to minimize alpha, right? Because that would be a false positive error, right? Incorrectly ascribe, incorrectly accuse, incorrectly give something significance even though there isn't significance, right? That is a alpha error. So you want to maximize 1 minus alpha because if you minimize alpha, you would be maximizing 1 minus alpha. It's just that 1 minus alpha isn't really a thing. It doesn't have a label to it. You know how 1 minus beta is called power? 1 minus alpha is not really called anything. It's just a way of saying that alpha must be really, really little if 1 minus alpha is really, really big. Like 1 minus 0 would be 1. That's the biggest it can be. But if alpha was like 0.1, then 1 minus 0.1, now your thing is going to become 0.9, 0.8, 0.7 as alpha gets bigger. So that's all that question was testing. It was a very interesting way to use 1 minus alpha to really throw people off, even though 1 minus alpha is not a real thing on the table. The last thing here, a study is performed to determine the association between statin therapy and rhabdomyolysis, which is one of the side effects of statin therapy. The findings for 1,000 patients are summarized in the table below. What is the best statistical method for assessing the results of the study? Now, anytime you're given a 2x2 table, always make sure it's plus minus, otherwise redraw the table for yourself in the correct standard way. This is the correct standard way. You have plus, which is rhabdomyolysis, and minus, no rhabdomyolysis, and then you have plus, which is actual therapy or intervention, and this is no statin therapy. So this is the correct way of putting the table together. So now you can put your labels in. So this is basically true positive, true negative, etc. So they want to know what is the best statistical method for assessing the results of the study. Excuse me. This is actually such a common question, right? You always get questions on this kind of stuff where a lot of people, if you got a question like this, a lot of people would actually pick t-test. But when you get data like this, you have to go with the chi-square. This is categorical data, right? This is categorical data. You're not measuring the statin therapy dosage. You're measuring categorically how many people had the side effect. The outcome of interest is a categorical variable, rhabdomyolysis or not. There are two groups, statin versus no statin, and outcomes are two variables. So chi-square would be the best way to analyze the results of this data. T-test is used when you have means, when you have averages, right? When you have actual numerical, not categorical data. We're going to see that soon enough. UWorld has a question similar to that thing that we just did too. The next thing here is from Amboss. This one says, a rheumatologist is evaluating the long-term risk of venous thromboembolism in patients with newly diagnosed rheumatoid arthritis by comparing two retrospective cohort studies. In study A, the hazard ratio for venous thromboembolism was found to be 1.7 with a 95% confidence interval of 0.89 to 2.9. Alright? Study B identified a hazard ratio for venous thromboembolism of 1.6 with a 95% confidence interval of 1.1 to 2.5. Which of the following statements about the reported association in these studies is most accurate? And the answer is the p-value of study A is probably larger than the p-value of study B. I remember p you wanted to be less than 0.05. So how do you evaluate stuff like that from the question they gave, right? It seems like everything is so unrelated. We were talking about confidence intervals, and then all of a sudden we're talking about p-value. But I just told you there's two different ways to figure out if the data you collected from a research is statistically significant. And remember, statistical significance is not the same as clinical significance. Statistical significance means that your data was not collected with error, and your data was not just a result of pure chance. So p makes sure that it's not just by pure chance. You want chance to be less than 5%. Right? Then you know that the data wasn't really collected by chance. That and the fact that your confidence interval of certain things should not fall into certain areas are both heavily related. Look at what happened in this question though. For the first thing they said, right, study A, in study A the hazard ratio was found to be 1.7 with the confidence interval of 0.89 to 2.9. And notice that 0.89 to 2.9 includes 1. Right, includes 1. And that's going to be this thing right here. Right? Hazard ratio is the same thing as like an odds ratio. Right? Odds of you getting disease. That's the hazard ratio. That's why it threw a lot of people off. But they're telling you the odds ratio is between 0.89 and 2.9, and that includes 1. The other one here, right? Study B has an odds ratio or hazard ratio of 1.6 with interval of 1.1 to 2.5, which does not include 1. So basically, for study A, you would not reject your null hypothesis, and there is no significant data. The data is not significant at all, which is akin to saying that your p must be more than 0.05, because that's another time that your data was not significant. Right? So the 95% confidence interval of the hazard ratio for study A includes 1, and therefore is not statistically significant, so the p-value must be more than 0.05, and a lot of the data was probably just collected by chance or with error, and you need to increase power. In contrast, the 95% confidence interval for the hazard ratio or odds ratio for study B does not include 1, and therefore is statistically significant with the p-value of less than 0.05, and you would reject your null hypothesis. Right? Although the exact p-values are not given here, we can use the significance criteria to infer that the p-value of the study B must be less than 0.05, and the p-value of study A must be more than 0.05, and that's it. Right? So this is more ways of looking at data and more ways of testing how well you grasped what's happening. Right? So 95% mean should not include 0, and 95% odds ratio or relative risk should not include 1. If any of that is there, then you do not reject your null hypothesis. Your null hypothesis is not rejected, which means that your experiment did not really prove anything, and you just wasted a lot of money. Alright, so that just really sucks. The last thing is your meta-analysis and the Pearson correlation coefficient, which are pretty straightforward, but a lot of people make mistakes. Meta-analysis is a method of statistical analysis that pools summary data from multiple studies for a more precise estimate of the size of an effect. Also estimates heterogeneity of effect sizes between studies. Improves the strength of evidence and generalizability of study findings. Limited by quality of individual studies and the bias in the study selection. Right? Meta-analysis is really hard to do. You can't compare different data with each other if they were collected in entirely different ways, if some of the data might have been collected very erroneously, or it's really, really old, right? There's a lot of things you have to do before you collect data and pull it all together, right? Because you might have bad data, and then you might have really, really, really good old data. If you combine it all, your bad data might look good now, right? That's not a good thing to do. You don't want to do that, and it's still pretty often done to make research look good because it's such a big business, right? You're not going to get funding if your research came out bad and you were unable to reject your null hypothesis. So common statistical tests are your t-test, the ANOVA test, and the chi-square test. Those are the only three you really need to know for your step 1. There are more statistical tests, but these are the only ones you need to know for step 1, because these are the most common ones used in medical research. T-test checks differences between the means of two groups, and means are averages. Averages are numerical data, right? So basically something like comparing the mean blood pressure between men and women in any kind of big group. So two groups of data, right? There's a bunch of men who gave blood pressure, there's a bunch of women who gave blood pressure. You're going to have numerical blood pressure data, right? Compare that to categorizing the blood pressure as either high or low, right? So a bunch of men that gave their blood pressure, you either put it in the high or you put it in the low. And a bunch of women that gave their blood pressure, you put it in either high or low. That's categorical data. Categorical data requires using chi-square, right? Big difference between t-test and chi-square. In t-test, you might have numerical values like blood pressures ranging from 110 to 120, 120 to 130, etc., and then you would actually have an actual mean, a median, and mode, all of that. That's where you use the t-test. ANOVA stands for Analysis of Variance. Checks differences between means of 3 or more groups. So basically a t-test, but for more than 2 groups. That's it. Right? It's comparing the mean blood pressure between members of 3 different ethnic groups. Maybe you're looking at Indians, Hispanics, and black people. Right? If you're comparing the blood pressure of all of that, that's one way to look at it. That you have a ANOVA test that's going to be necessary now, because you have the same kind of numerical data with an average, right? You have the mean, but it's more than 2 groups. So now you use ANOVA. Very easy. This is actually really, really easy, but it's so easy to make mistakes on as well if you're not thinking correctly, right? Remember to make the difference between a mean and a categorical data. Categorical data does not have numerical value to it. Means have numerical value to it. The last thing, and probably the most easy thing to understand in all of first aid, is your Pearson correlation coefficient. R is always between -1 and 1, because that's the slope of a line, right? Either the slope is -1 or the slope is +1. The closer the absolute value of R is to 1, an absolute value is a mathematical thing, where remember absolute value is the distance from 0, right? The actual definition of absolute 0 is the distance from 0. Colloquially, absolute 0 basically meant that you take the minus sign away. So the absolute 0 of -90 is 90. The absolute 0 of -75 is 75. The absolute 0 of 60 is 60. The closer the absolute value of R is to 1, the stronger the linear correlation between the two variables. Right? So you can see there's a really strong correlation here. The line is -1, so the absolute value of that is 1, and all the dots are falling on the line. Right? And same thing here. Correlation is very good here. Strong positive correlation, strong negative correlation. Right? The difference between the first and last picture is that this is called a negative correlation because things are going downwards. The slope of this line is negative. Yes, the correlation is very strong. The relationship is very strong between the two things. However, what you're noticing is as whatever is on the x-axis is increasing, then whatever is on the y-axis is actually decreasing. Whereas over here, as whatever is on the x-axis is increasing, whatever is on the y-axis is also increasing. Alright, so that's what it's called negative or positive correlation. These are weaker, and this has no correlation. You cannot draw a line here at all. Nothing is following the slope. Positive R value means positive correlation, so as one variable increases, the other also increases. Negative R value or negative correlation like this one means as one variable increases, the other decreases. Coefficient of determination is the only thing you can really calculate here, and that's basically R squared. Right? Amount of variance in one variable that can be explained by variance in another R variable, R squared. Variance was also SD squared, standard deviation squared, when we were looking at statistical data up here. Right? We said variance. Variance is SD squared. Variance is always that number squared. Standard deviation is the variability between data. R is also the variability between data, right? If the data is not very variable, the number is going to be much closer to 1, and R squared is still going to be 1. So that's all that's happening there. Here's another question where the answer was meta-analysis, right? Let's see how they face this question. It's a little blurry, so I'll read it out. It says, a meta-analysis of several trials on the effect of cocoa intake on systolic blood pressure revealed the following results. And then you have this weird looking table that really wants to throw you off. And you're just like, shit, what the fuck is this? Then you read the question. All the trials evaluated the difference in systolic blood pressure at 2 weeks. Based on the data, which of the following is the most appropriate conclusion? So before you can even look at all the conclusions, you need to make sure you understand what's happening in the data, right? Don't make it look like Arabic and you can't read Arabic. Make sure you can read what's happening in the data. So they tell you there's G different study groups, and the mean systolic blood pressure in cocoa group minus the mean systolic blood pressure in the control group is being given. And then within brackets, they're giving you your 95% confidence interval. So look at all the different 95% confidence intervals. So the first one, negative 7.3 to negative 3.4, negative 5.3 to 10.4. This one here is going from negative 5.3 to 10.4. And we're looking at the mean. Confidence interval of mean, remember, should not have 0. Right? An average should not contain 0. Right? Remember, we just did that right here. 95% interval for mean difference should not have 0. If it does have 0, you will not be able to reject your confidence interval. So negative 7.3 to negative 3.4 does not have 0. Negative 5.3 to 10.4 does have 0. Negative 8.1 and 2.7 does not. This one also does not. 0.1 to 1.2 does not have 0. So that's good. Negative 1.2 to 3.3 does have 0. And then you do the total calculation, and the total, getting everything added together, also does not have 0, right? Negative 2.7 to negative 1.3, no 0. So because the total does not have 0, this is good, we're okay. So our 95% confidence interval of the mean does not have 0. Now we can actually reject our null hypothesis. So whatever answer says reject your null hypothesis or prove what you set out to prove correctly, then you're good to go. So a higher mean systolic blood pressure was seen in the cocoa groups overall. A higher mean systolic blood pressure was seen in the cocoa groups overall. Well, mean systolic blood pressure in cocoa group, we don't have the data to see what's been seen in just the cocoa groups, so we can't even pick A. Doesn't make sense, right? Cocoa intake should be recommended for blood pressure management. Again, we can't really see if cocoa intake should be recommended for blood pressure management. It looks like the difference in blood pressure between the cocoa and non-cocoa was only really negative 2.2. So doesn't seem like there's much of a problem. So cocoa intake should be recommended for blood pressure management. Mean systolic blood pressure in cocoa group minus the mean systolic blood pressure in control group. It does look like the cocoa group must have had a lower blood pressure, which is why the difference is negative. But it doesn't seem like B is very plausible because we're not really seeing any kind of major help in terms of blood pressure management, right? If the blood pressure was going down significantly, like by 10 or something, then maybe. This last one, answer choice C, says cocoa intake was associated with a statistically significant decrease in systolic blood pressure. This is true, right? We just saw from the total, right? You didn't even really need to look at all of them, but I wanted to show you guys. But we just saw from the total, the ultimate statistical data, that 0 is not included in the 95% confidence interval of the mean. So the data is statistically significant. So the data is statistically significant. C should be correct. D. B, F, and G showed a statistically significant increase in systolic blood pressure. B, F, and G. Well, F is the only one of those three that did not have 0. B and G do have 0 in their 95% confidence interval. So D is false. E, there was no statistically significant change in blood pressure, and 21% of people chose that. But that's false. There is statistical change. There's a statistical significance to this data because 0 is not in the 95% confidence interval, so we're just going to pick C. even though we couldn't really rule out B, C definitely seems like the much more correct answer. Right? And then they went on to explain a meta-analysis groups the results of several trials to increase statistical power and provide an overall estimate of the effect of an exposure. So we took many different studies and put them all together to make our data more significant. The individual results of the trials are assessed and weighted to obtain a pooled effect estimate. In this example, the results of the meta-analysis showed that there was an overall change in blood pressure of negative 2.2. So decrease in blood pressure, right? And we did understand that. We understood that from the question that this means blood pressure went down by 2.2 because most people who took cocoa the number 2.2, negative 2.2 was achieved by subtracting the blood pressure of someone who took cocoa from someone who did not take cocoa. So that means that this number must have been less than the number of people who took cocoa. So this might have been something like 100. This might have been 102. Right? So 100 minus 102 would be negative 2. Something like that. Right? So the blood pressure did seem to be lower in people who were taking cocoa regularly. In this example, blood pressure goes down by 2.2 in the cocoa group compared to the control group. The corresponding 95% confidence interval, which is a measure of statistical significance, was negative 2.7 to negative 1.3. This range does not include 0, which is the null value. Therefore, the result is statistically significant. In summary, cocoa intake was associated with a statistically significant decrease in systolic blood pressure. Right now, some company that makes a brand new cocoa can actually put it on their box, helps with blood pressure, might reduce your blood pressure, blah blah blah, and they can advertise themselves. Right? This kind of research is a very real thing in the business world. It occurs every day, and people use it, people abuse it, all kinds of stuff happens. Another question here was about the chi-square versus t-test stuff. So a study was conducted to assess the association between simvastatin therapy and serum fibrinogen levels in patients who undergo percutaneous coronary interventions. Serum fibrinogen levels are recorded as either high or normal based on a specific cutoff. The data is presented in a 2x2 table with fibrinogen being high or normal with regards to simvastatin therapy. What is the best statistical method for assessing the results of this study? And 57% of people got it right by picking chi-square test, because this is categorical data. There's no numerical value. 32% of people, though, chose the 2-sample t-test. And that's not what you do, right? This is not a t-test thing. This question is actually very similar to the other one we just did up here, which also spoke about statin therapy, right? And rhabdomyolysis this time, but again, no numerical data. This was all categorical data. Categorical data means you pick chi-square as your answer choice and you're done. If there's numerical data and there's a bunch of averages and stuff that you can compare, then you go with your t-test. Alright, so that wraps up all of biostatistics. Make sure you go over it again. This is not something you'll master and learn once. And make sure you also do practice questions where you utilize this. And the third thing I need you to make sure of is to draw this out for yourself and start getting used to being able to draw out the entire cheat sheet without having any issues. All the equations should be something you have muscle memory of as well as retained memory of. And you should be able to understand the Gaussian curve. You should be able to understand data from any 2x2 table, no matter what it is. And you should be able to evaluate things from that 2x2 table using whatever correct formula is necessary. And truly memorize confidence interval, right? Because they give you a lot of data, but if you don't remember how to use the data, then that data is useless to you, right? Know how to calculate confidence interval. Know what should not be in the confidence interval, and you're going to be much better off with any of these questions. They're really easy questions, but they become significantly hard questions if you didn't really study enough. So that's all that's happening there. Alright, and then in the next video we'll go into looking at something that a lot of people find confusing, ethics.